Hello class. In this lesson we'll be reviewing transformations, and we'll also be looking at dilations from the perspective of a transformation. First, I'd like you to write down the definition of a transformation and try to do it using function notation. So try that and I'll show you my solution. So here's the definition we have for a transformation. We are inputting a point and the output is a unique point. So if f is our transformation, we input p, and the output is p prime, or f of p, which in this case, we talk about its image as p prime. So f of p, the output, that's the same as our point p prime. Okay, every point has an image. And we talked about rigid motions before. Why is that word important? What does the word rigid refer to? Well, rigid is referring to the fact that we have an isometry. That is, the distance is preserved under the transformation. And we also learned that lines map to lines, rays to rays, segments to segments. Angles map to angles, and the angles measures are preserved. Okay, those are all important properties. So let's actually go through and review some of these transformations. So here's an example I'd like you to try. I'd like you to draw this on a piece of graph paper and see if you can find the center of rotation and the angle of rotation. So how do we find the center of rotation? Pick two corresponding points, and you find the perpendicular bisector of the segment that connects them. You do that for another pair of corresponding points, and where they cross is the center of rotation. And to find the angle of rotation, you connect that to two corresponding points and measure the angle. So for example, in this problem, it turns out that the perpendicular bisectors, we did it here with BB prime and DD prime, those intersect at the points 4, 1. And to figure out that angle, connect your center of rotation to two corresponding points. We picked D and D prime here, and measure that angle, and it ends up being 60 degrees. Start with 0 on here, over to 60. And we're going counterclockwise, so we don't have to specify anything else. Okay, let's review lines of reflection. So how do we find the line of reflection here? And then how do we figure out where P maps to? So try that. So to find the line of reflection, you pick the two corresponding points, A and A prime, and you draw the perpendicular bisector of that segment. And that's this line here. And to figure out where P maps to, you draw a circle around P. I'll demo that right now. Draw a circle around P that crosses your line at least one time. You can just draw an arc too. So that crosses the line twice. And then you put your pivot on one of the points of intersection and open up your compass to the points. It's pretty much there. And you can draw a circle there. And then repeat the same process at the other point of intersection. Right, double check that your compass is on the point, draw a circle, and where those two blue circles intersect, that gives you P prime. And finally, we have a translation. Point C is the image under a translation. We want to figure out where the pre-image is. So we want to find the coordinates of C if we use the vector BA. So if we use vector BA, that means we start at point B and we're pointing to A. So our direction is down to the left. So if C prime is the image under that translation, what's the pre-image? It must be the point 1, 6. Now what if we had used the same distance but the other direction? What if we had used vector AB? So if we use vector AB instead, that means we're starting at A, going towards B. So it'd be this vector. And so if C prime is the image under that translation, you have the point -5, 4. So the direction is important in a translation. So what do we have in common with these three basic predictive motions and dilations? Well, they all follow that same rule for a transformation. We all input, for every point we input, we get an output on the plane. And dilations and rotations, they both have centers that we talk about. Okay, so these are all different types of transformations, but how is the dilation different? Well, the dilation, it doesn't preserve distance. It's not an isometry. If the scale factor is not 1, then distance will not be preserved. So you know the distances are scaled, they're all proportional, so they're not equal. And just like we have with the other transformations, we have an inverse for our dilation. So let's think about that for a moment. If we perform a rotation around O, 90 degrees around O, how do we go back to the original point? We would just turn around O, but now use negative 90 degrees, go in the other direction. So if you do those two rotations, you end up with the original point P. How can we do something similar with a dilation? For example, what if we did a dilation of 2 with the center O? How would we go back to the original image? So how can we go from doubling the lengths to going back to the original? Well, we would use a scale factor of 1/2. You can just multiply those scale factors and you'll see that you end up with a scale factor of 1. So the inverse dilation is going to have the same center, but the scale factor is going to be the reciprocal of the original one that you used. Some more practice with the dilations. We want to find the center of dilation, and we want to find the scale factor. Try that, and I'll show you the solutions. So, to find the center, you connect the corresponding points, and these intersect at O. That's our center. And so to figure out the scale factor, you're going to divide from the distance from the center to a point in the image, so A prime for me, and from the center, divide that by distance from the center to a point in the pre-image, the corresponding one, A. So your numbers might be different for your actual measurements. That's okay. So in this case, I end up with 3 centimeters from O to A prime and 1.5 centimeters from O to A. So my scale factor in this case is 2. So depending on how you did your dilation, you could have a different scale factor or your numbers might be different. But still the same idea. In this case, we want to actually do the dilation. We want to compare the length AB with length A prime B prime. So you can do this using the ratio method. You would measure length here, OA, multiply that by 3, and find A prime on right OA. Measure from O to B and triple that, and then find B prime on right OB. And with these measurements, I end up getting 12.6 and 4.2. If you divide those, you get 3, and that's the same as the scale factor. So you know that all the sides of the triangle are going to be scaled correctly. And finally, what happens with angles when we do a dilation? So we're going to use a scale factor of 3 here. Multiply those distances by 3, and you get this picture. What do you notice about our angles? They are 60. They're equal measures. So far we know about 2 types of transformations. We have the isometries, and we have the ones that aren't, the dilations in this case. They don't preserve distance, always dilations. So, but they're similar in that we are inputting a point, and they're assigning that to a point, another point on the plane. And we can always find those inverses. Thanks for watching this video.